Okay. Right. So we've only got three problems that we're going to do today, but they're sort of the more involved related rates problems. Um, yeah. But I guess before doing that, are there questions on anything? Anything you want to go over before we get started? No? So I actually released the videos. Yeah. I mean, some people don't look at emails though, but yeah, I released the videos Tuesday evening. So yeah, you hopefully if you had questions on the exam or if you question like how they graded you, you want to see what the real answer is. Those videos will have it. But all right. So number five. Let's see. We've got a person, a height, and so this problem is one of the similar triangle problems. Uh, the best thing to do is to start by drawing the situation here. We have some street light that is 8 meters, and we have a person that is 2 meters, and there's a shadow that's being cast. So that's what makes the triangle, uh, the similar triangles. Let's just extend that a little bit. Okay, and so we know that the person is moving at a speed of 0.5 meters per second, or 1/2. Um, so now the question is, what do we want to label uh, as being, like, what things should we label? And I'm gonna follow what I did here. I'm gonna label this guy D for distance from the person to the street lamp. And the length of the shadow is actually going to just be this part, okay, this side. So um, then what this is saying about the person moving, it's saying that the ds, or well, d prime. Okay, so thankfully if we use the prime notation, we're not going to be confused, because otherwise this would be dt, and that's kind of we're being redundant, or we're sort of using d for two different things there, which is kind of confusing. But with the prime notation, it's pretty clear. Okay, so now d prime is 1/2, and then units are meters per second. Uh, okay. So this is the data that we have, and we also need to set up an equation that describes the system for all time, imagining that this picture is evolving, right? Imagining that the person is moving along, and that the shadow length is also therefore increasing. So, and the equation that we're going to set up is going to involve these similar triangles. Okay, so hopefully you can just see that we have a, do I want to just draw on top here? Well, no, I'll just use my cursor. So you can see, like, you've got this small triangle here, and then you've got the big triangle there. And what we'll do is we'll set up a proportion um that relates things. So what I'll do is I'll say that s over 2 is equal to, do I want to do that? Yeah. Okay. Yeah. S over 2 is equal to the s plus d over 8. Okay. So we know that is true just by similar triangles. S over 2, s plus d over 8. Okay. So this holds true by geometry, and it's going to hold true regardless of what time what snapshot in time we're going to be considering. Now, what we want to do is basically, I don't like the fact that you've got two s's there. I'd like to combine the two things, and I'd like to do that before taking the time derivative. So basically, like, if you can ever do any algebra to simplify whatever function you're working with, or equation in this case, do the algebra first before you do the calculus. Just, it makes life a little bit easier. Okay, so here what we'll do is we're going to split the denominator and then move things to the other side. So you're going to have s over 2 minus s over 8 is equal to 1/8 d. Okay, and then the left-hand side we can calculate. That's just 3 over 8 s equals 1 over 8 d. Okay, and so this equation is what we then take the time derivative of. We do a d dt to that. And so then we get 3/8 s prime is equal to 1/8 d prime. where the primes in this case are derivatives with respect to time, right? And then from this point, let's well, I can just move the thing over. And I'm trying to calculate what? I'm trying to calculate what rate the person's shadow is increasing. So I'm trying to find the S prime. Okay, well, we're very close to that. If I just move this over and then I plug in my D, I'm gonna get the answer. So I'll get 1/3 times the 1/2. Wait, that doesn't look right. I think I did this wrong on paper. I'm supposed to do, yeah, I'm supposed to get what I'm getting right here. So I get 1/6 meters per second. Let me just double check everything since it seems that I didn't match my previous round of doing this. Yeah, this should be right. Yeah. Okay. Does that make sense to everybody? How I went through this whole process? Any questions on any of these steps? Okay, I got a thumbs up, so just one thumbs up though. So hopefully everyone else is okay. I'm gonna keep going if interrupt me. All right. So number 6, actually number 6 isn't so bad. As long as you know, as long as you're comfortable with the trigonometry. So, right. For this one, we've got a hot air balloon and then an observer. So again, this is a triangle, but in this case, you've got maybe should I use height? Maybe I'll use H for height. The thing that you're actually doing is you're trying to figure out things involving angles. So you have a theta here, and it's specifying that the specific moment in time is given by the theta equals equals pi over 4. And so, okay, let's translate this. When theta equals pi over 4, theta prime is equal to 1/10 radians per minute. That is this second sentence. And it wants us to figure out how fast is the ball rising in that moment. Find H prime. And we're given that the observer, which is this point here, is the observer is located 2 miles from the liftoff point. Okay. Right. So we have a hot air balloon that's rising. We're tracking the angle of inclination that we need to view it from. And yeah, we want to figure out just by measuring, I guess, the head tilt or whatever recording tilt, you can calculate how quickly something is rising. Okay. So we need to then formulate some kind of an equation that relates these quantities, this H with this theta. And so there should be a specific trig function that comes to mind, right? And I'll just ask you, what trig function should I use?
Would it just be tangent?
It's tangent, that's right, yes. Yes. So the equation you'll write down involves tangent of theta, and that's going to be H over 2, exactly. So you can imagine as, regardless of what picture you're drawing, this equation is going to hold true, right? Okay, now we go ahead and take the time derivative of this equation. There's not really anything else you can do at this point. So d dt. So that's going to turn this into a secant squared theta times theta prime. Remember, this is implicit differentiation. The theta is something that changes over time, so it's the way it changes with respect to time is something that is non-trivial. So you have to write the theta prime there, and then the h also you have h prime. Okay, and let's see, we can actually plug in almost everything, but there is some little tricky thing here involving this secant squared theta. So what we have to do is a sort of a side calculation here. Okay, so this is the dynamic picture that I've drawn. Let's now draw that specific snapshot in time. Let's draw the static picture. So in the static picture, we've got that the theta is actually supposed to be pi over 4, a 45 degree angle. And this is 2, so we actually know this is 2. And then, of course, we can use Pythagorean theorem to say that this is 2 root 2. So the whole point of this is because we actually need to calculate what is this secant squared of theta. Now that I've drawn the full triangle, we can then figure out what the secant squared should be, of theta should be. So cosine, we'd start with cosine, and then we would reciprocate it, and then we would square it. That's the process to calculate this secant squared theta. So cosine in this case is adjacent over hypotenuse. It's just 1 over root 2. Secant, therefore, is the reciprocal, is root 2. And so then when we square it, we get 2. Okay. So that gives us this value over here. We get 2 times, and we're given theta prime, 1 over 10, equals 1/2. And then h prime is actually the thing we're looking for. Okay. And so now we just go ahead and solve it. Very easy. 4 over 10, so that's 2 over 5. Wait, pi. So, something's funny here. Oh no, I'm looking at the wrong problem. Okay, yeah, 2 over 5, yes. And then units, right? So the distance measurement, the unit for distance we're using is miles, and then the time unit is minutes. So it's a bit funny, miles per minute, but that's what this problem is in terms of. So there we go. I can't box things. Okay. All right. Any questions on that? It's going to be a very short class if no one has any questions. Maybe that's what you want, a really short class. Okay, well, then number 7. All right. So this one is the one where there's sort of a trick to it. There's kind of 2 ways to do it, and you could call one the clever way. You could call one the long way. Yeah. So we have a conical tank, which for some reason is always depicted like this when you look in the textbooks. And the height is going to be 10 feet. And the radius is 5. And you've got the water is flowing into the tank at a rate. So this is actually change in volume. V prime is equal to 2 feet cubed per minute. And we want to know the height level. So I'm going to then like just pretend there's that, and this is the height that we're after, and there's going to be some radius that corresponds to that. Find h prime when h is equal to 4 feet. So that's what the problem is asking us to do. Okay, so well, it's pretty clear that what we need is some formula for volume of a cone. And we can do, oh, now I see why we draw it this way, because the frustum is harder to calculate. Okay, so yeah, volume of a cone, 1/3 pi r squared h, right? So I don't know, geometry, right? This is, so if you remember the formulas for geometrical figures, like you kind of remember this thing. If not, it's like the idea is that the volume of a cone is always 1/3 the volume of the cylinder, and cylinder is just base times height. So the pi r squared corresponds to the base, and then can I go back to 5? Yeah, okay, I'll go back to 5 after this. Fine. Yeah, so area of the base times the height gives you the volume of the cylinder, obviously, and then you divide by 3 because for some reason cones are just divided by 3. There is a reason for it. It's kind of I don't think there's a very good geometric intuition for it. I think actually the first way they realize this is you have to do some kind of calculus to arrive at that formula. But anyway, so right now this is where things kind of branch off. We have this formula, and what you'd be tempted to do at this stage is to take the time derivative of this formula. Okay, but when we do that here, it's going to get kind of complicated because you've got a product rule here. So you're going to end up with a product rule that uses r and h as well as r prime and h prime. That's the long way of doing it. You can totally do it that way. And I probably, I should encourage you to at least give it a go and do the long calculation and make sure that the short calculation will match up. It's just a good practice. But what I'm going to do is I'm going to do the shortcut. Although with all this extra time, I probably could also do the long way. The shortcut is to realize that actually R prime and H prime are going to be related to each other because the quantities R and H are related to each other in this picture. Because you have similar triangles working around, you're going to have a relationship between R and H. Then you take the derivative of that equation. That'll give you an equation relating R prime and H prime. And in fact, what we'll be able to do is we'll be able to replace one of the variables here. We'll be able to replace R with H. That then take the derivative of volume, treating volume as a function of H only. Okay, so let's do the similar triangles thing. Okay, so we have what's this? 5. I think, yeah, if I just 5 here, and then this guy is 10, and we're interested here. This is R, and this piece is H. So the similar triangles, I'm just going to ratio the corresponding sides. So R divided by 8 is going to be equal to H divided by 10. Right? Wait, that's not supposed to be 8, that's supposed to be 5. I can't read my handwriting. It is 5. Yeah, it is 5. Okay. Actually, I don't even need to take the derivative of this. It's easier if I just use this. This relationship lets me replace one of these variables. Yeah. See, if you do trickier problems, you might need to replace the derivatives instead. I was thinking I was overcomplicating this. This is easier than I thought. Yeah. So this equation tells us R is equal to 1/2 H. Might be better to just say this is actually H over 2 because we're going to end up squaring this guy. H over 2. Okay. Yeah. So this relationship lets us replace R in this formula. Okay. So we go ahead and do that. That will simplify our calculation, simplify our lives a little bit. So we end up squaring this guy, and then we'll have a H left over. So let's just combine all that together. We get a H cubed over 4. Okay. And so we have V now is equal to all this. And now we can take a time derivative, and it makes things a lot easier. D dt. Okay. But so I'll give a bit of a warning about this. Like how the reason that we really could do this replacement is because the way that the quantities R and H are related to over time, there is a relationship there, right? If these factors were changing independently of one another, if it wasn't just the height of the cone that was changing, but also the angle of the cone, if both of these things were changing in some nonlinear, some weird fashion, then you wouldn't be able to do this kind of simplification. You wouldn't be able to simplify this formula, and that would force you to actually do the product rule that I was describing. The long way would be the only way of doing it. Here, because there is a relationship, we can actually do a replacement and simplify the equation. Okay, so now we go ahead and we take that time derivative. We get v prime is equal to, and then here, well, this 3 is going to cancel this 1 over 3. So I'm just going to get pi over 4 h squared, h prime. Okay, and let's see, we're given v prime. So let's 2 is equal to pi over 4. We're given that h is going to be 4, so 4 squared h prime. Okay. Can I solve that in my head? 4 divide. I think I'm just get. Wait, hold on. I just got 1 over 2 pi, which is just not looking right to me. 4, 2, 1 over 2. Is it supposed to be 1 over 2 pi? Did I do something wrong? Yeah, okay. I guess I wasn't paying attention when I first did this. So I'm getting 1 over 2 pi because I'll get a 1/2 here and then I'll divide by pi again. Yeah. And this is measured in terms of feet per minute. Okay. right? Does everyone agree on my calculation? Just you should be double checking me if I make silly arithmetic mistakes. I really forgot to square this up here. No? Okay. Everyone agrees. That's good, I guess. I'll blame it on you if I have to find all that I actually did make a mistake. All right. So yeah, number 5. Someone was asking me to go back to this. Yeah. Did you want to ask me about this?
I was just wondering about the, I was just confused about the order.
What order?
Or I mean, yeah, I mean, I get it now from seeing it, but I was just confused earlier.
Okay. All right. Any other questions? Wow. Okay, well, if not, then we'll end early for today.